So in lecture 2.5, we're going to continue our exploration of computational Boolean algebra, only now we're going to take it in a slightly different direction. We've been working very extensively with the cofactors and seen how powerful and important and useful those things are. But what we really haven't given you yet is a concrete data structure, a way of actually representing the Boolean object in a way that we can manipulate. And so we're going to do an interesting application which is called tautology. And tautology is a particular question you can ask of a Boolean equation. And that question is it 1 all the time? And it turns out that it brings together all of the interesting things we need to see how a computational view of Boolean algebra, a data structure and operators view of Boolean algebra come together. And it also shows just a lot of the skeleton, the style in which a lot of computational Boolean algebra operators are actually done. And we're going to use these ideas extensively later in the course when I show you some other data structures and other important operators. So let's go talk about recursive tautology. Here in lecture 2.5, so what exactly is tautology? It's actually an interesting problem. I'm going to give you a representation, some sort of a data structure that can represent a Boolean function, and you're going to build an algorithm that operates on this data structure, and you're going to tell me a yes/no answer to this question. Is this function f that you've given to me and represented in this data structure equal to 1 for every input? And I know what you're thinking. I know exactly what you're thinking. You're thinking, Rob, how hard can that be? The function is 1 every place. And the answer is very hard. What if I give you a function that has 50 variables? What if that function has 117,000 product terms? And it just happens to be that every single one of those product terms covers every single one of the rows, of the squares in a Carnot map. That's not easy to do. We're going to need some kind of cleverness to be able to calculate something if you give me a Boolean expression to calculate tautology. This turns out to be a great example because it illustrates all the stuff that we need to know to be able to solve problems like this in an efficient way. So we're going to use a simple early representation scheme for functions. We're going to represent the function as a set of ORed product terms. And so the idea here is that it's the OR and the product are really the things that I'm going to specify. Now this is really nothing more than a sum of products, but done as a very particular kind of a data structure, a practical, computationally viable kind of a data structure. And as a simple visual for this, I'm gonna describe these things using a three-dimensional Boolean cube. It's helpful when you're looking at any literature about this stuff. You'll see these things all over the place. You can think of this as really just a way to graph a small Boolean equation. So this is really a set of axes, right? And so there's the a-axis. And there's the b-axis, and there's the c-axis, right? And that's the value with a as a 0, and that's the value with a as a 1. And this up here says that this corner, this vertex, has the value abc equals 1, 1, 1. And clearly you can only have values of the graph at the vertices, right? Because it's discrete, doesn't exist in between. And we put a solid circle on the vertices where the function makes a 1 there. It's a simple Boolean cube. And when we talk about product terms, just like in a Carnot map, we're going to call them cubes. And they're really just groups of 2 to the k adjacent corners that we can circle where the function is 1 everywhere. So suppose that the function I'd like to represent is a bar plus bc plus ab, right? Then I could circle, there's a bar, and I could circle bc, and I could also circle, that would be AB, and that would be my representation. And one of the things that I will note is that this is not necessarily minimal. And indeed, if you look at this, there are better ways to cover this, kind of obviously. There's actually some better, bigger ways to cover this. So no guarantees that this is minimum or the most efficient representation, just that it can be correct. So when we say cube, that's what we mean by product term. And the way we're going to represent product terms is in this historical representation called positional cube notation. So it's a little vector with a slot for every variable, and there's 2 bits per slot. And there's just some simple rules. If the variable appears in true form like x, you put a 0, 1 in the slot. If it's complement form like x bar, you put a 1, 0 in the slot. If it does not appear at all, you put 1, 1 in the slot. And you just don't use 0, 0. Turns out you don't need it. And the basic way to think of this is just to give me a little example, right? So here's A bar. A bar would be represented as this little vector with a 1, 0 in the A slot, a 1, 1 in the B slot, and a 1, 1 in the C slot. All right, that's how you would represent that. And if we did, let's say this one, this is BC, right? So BC would appear as 1, 1. There is no A there. And O1 because there's a B, and O1 because there's a C. So that's positional cube notation. So why the 2-bit slots? Well, it turns out that if you use this representation, you simply AND two cubes together, slot by slot, and you just AND the bits together, it does the right thing. And also, kind of, interestingly, if you AND two cubes together, and the result should actually be 0, right? That the cube just goes away. What happens is you actually get one of these 0, 0 values, right, in the slot, and that's a signal to you that says, oops, this cube doesn't really exist. So it's like you took a cube with an X in it, and you ANDed it with a cube with an X bar in it. You'll get a 0, 0 in a slot, and that's the signal that says, hey, kill this cube. I don't need this cube anymore. So you'll never see it sitting around in a static cube. You'll only see it if you're doing computations. So it's a very nice, very simple, very useful kind of a formulation. So we will represent a function as a cover of cubes, just like a set of things you can circle the ones on in a Carnot map. And this is really just a list, right? And the list is how we're going to do the OR of the product terms, right? And the positional cubes are how we're actually going to do each of the products. So if we have this function again, I'm sorry, that should be a bar. Then what actually happens is that here's the A bar, and this is that cube, right? And here's the BC, and it's that cube, BC. And here is the AB, it's that cube. Each positional cube notation vector represents one product term. You put a list of them together. Doesn't matter what the order is for the list, by the way. You just got to have them in the order, in the list somewhere. Doesn't matter the order. This is our representation for something that's basically a sum of products kind of a form. So next question. How do we approach tautology as a computation? Well, it turns out that cofactors are basically what saves us here. Right, so there's a wonderful, great result. And the result is as follows. A function f is a tautology if and only if both of its positive and negative cofactors are also tautologies. So this makes sense. Suppose it's the case that the function is 1 everywhere. Well, then surely it must be the case that the function when you take x as a 0, or the function when you take x as a 1, must also be 1. Right? So both of the cofactors are also 1. So it works that way. And what if both of the cofactors are a 1? Right? Both of the cofactors. Well, we know by the Shannon expansion theorem that we can always represent the function in that nice little decomposition, right? But we know that that cofactor is a 1 and that cofactor is a 1. And so you just get, well, you get x plus x bar and it's equal to 1. So it works the other way. So it works this way and it works this way. And it's a great result because it gives us a computational decomposition strategy. What happens if the function I'm looking at is too complicated to just tell if it's a tautology? Break it up into 2 pieces and answer the question on the 2 smaller cofactors. And you know that the original function was a tautology only if both of the cofactors are tautology, so recursively compute that. So you can take a hard problem and make it into 2 simpler problems with a strategy for gluing the answer back together if you know the answers for both of them. That's just basically what this picture says. If you cannot tell immediately with some simple mechanics that the function is a 1, pick a variable, split, and go ask the question on the positive cofactor, and then go ask the question on the negative cofactor, and you combine them with simple, kind of 1-bit Boolean function. Are both of them 1? Yes or no? Yes, then I'm a tautology. That is an amazing thing. It gives us a strategy for doing something very complicated. So the things we're going to look at next are, as an algorithm, what are all the steps in the process to actually make this a real computation?